Hello everyone, let's move on to part 2 of module 3, that is signal encoding techniques. In part 1 we already seen the different signal encoding techniques, including the 4 categories: digital data to digital signal, digital data to analog signal, similarly analog data to digital signaling and analog signaling. So and these 4 techniques, they are relevance and some basic idea like terminologies, everything is are familiar with. Now we are just seeing each technique in detail, starting with the very first category that we already seen. It is one of the simplest scheme, and so it is less complex, less costly. Those things we already seen, because that is very clear, right? Because digital data you are trying to convert to digital signals, both are digital. So see, some set of binary information is coming, and that binary information you are converting it into a binary signal. So for 0 and 1, some voltage level you have to fix, and accordingly you have to proceed. So but if you are simply proceeding, there are certain problems that we will see, and those things you have to tackle here by making that process of conversion of digital signal into digital data into digital signal. Means try to do it in a more intelligent way, so that certain problems with the so we simply will think like we have a sequence of ones and zeros. So for one on voltage level, for 0 another voltage level, so simply convert like that. But if you are doing in a straightforward way, there are certain problems that we will see, and to overcome those problems we will try to make it in somewhat different way, and those techniques in detail we will be studying here. So first we will familiarize certain terminologies here, starting with the term signal element. So a digital signal is a sequence of discrete continuous voltage pulses, right? And just like so each such pulse is known to be a signal element. So it is like the part of the signal which is completing a cycle, something like that. So you can see a series of discrete and discontinuous voltage pulses in a digital signal. Okay, so that is clear for you, and each pulse of voltage is known to be a signal element, and within the signal element you are trying to encode a data element. Okay, signal element and data element. So binary data are transmitted by encoding each data bit. So when it comes to binary, we have bits by bits, binary digit, right? Each data bit has to be converted into a signal element. Accordingly, the form you are deciding for the signal element. So in the simplest case, there is an one-to-one correspondence between the bits and the signal elements. So this is what I said. This is what is a default picture that is coming onto our mind. That is our mind. That is the simplest case, where there is an one-to-one correspondence between the data bit and the signal element. For 1 on voltage, for 0 another voltage, like that. So that is the simplest form, but we have more complex structures here. That is having some additional function features compared to the simplest form. Now in such a case, we have a broad classification of this digital signal, digital data, digital signal technique, like unipolar technique and bipolar or simply polar. So what about unipolar? Is the polarity, that is a voltage level. If you are looking at this single polarity, like if the signal elements have all same algebraic sign, either all the signals are of representing in the positive voltage, you are not going to the negative part, or all the signal data element like zeros and ones, everything is representing the negative polarity, that is all positive or negative, that is called a unipolar. That means you are not changing the logic state like positive and negative voltage level, like that. Not, you are not giving the positive itself. You can vary the level of the signal, like for 0 say plus 5 volt, for 1 say plus 2 voltage, like that you can represent. Simply I am giving an example. So if you are, or for 0 and 1 fix 2 voltage level, that is of negative polarity. So that is a case, that is what we are calling as unipolar system. But mostly in practical cases, we are using bipolar system, or simply bipolar system is otherwise called polar. So polar means bipolar. Okay. So when it comes to polar signaling or bipolar signaling, one logic state is represented by a positive and another logic state is represented by a negative voltage level. So say plus 5 for 1 and minus 5 for 0. Or in any way, I am just taking an example. So like that, if you are representing, you are giving two different polarity for two different bits, then it is called polar signaling. Okay. So digital signaling rate or bit rate of a signal is the rate in bits per second that the data are transmitted, and this also means most of the terminology you are already familiar, right? So bit rate means the rate at which the bits are transmitted or the number of bits transmitted per unit time. So bits per second, how many bits are transmitted per second? Okay, so that is called the bit rate or the data rate or data signaling rate. Okay, I'm just making you familiar with the terminologies here and the techniques we are going to deal with. So another terminology is duration or length of a bit. Okay, so what is length of a bit? Is the amount of time it takes for the transmitter to emit the bit. We saw another terminology for it, that is a transmission time. So how much time it is taking? Not transmission time, sorry, transmission time is the time taken to transmit a complete frame, a sequence of bits. Here it is the bit duration, how much time you are taking to transmit a single bit. Okay, duration of the bit or bit duration or length of a bit. And if the data rate is say r, data rate is r means in every second you are sending r bits. Okay, r bits per second. So in 1 second you are sending r bits. Then for sending 1 bit, how much time it will take? 1 by r second. Okay, if data rate is r bits per second, what does it mean? In every second you can send r bits. So 1 second you are sending r bits. So how much time you will be taking to send 1 bit? 1 by r second. Okay, so that 1 by r will be the bit duration if r is a data rate. Now similar to bit rate, another terminology we are using is baud rate. Baud rate, it's also called modulation rate. Okay, in contrast, is a rate at which the signal level is changed. So here we are purely dealing with the number of bits transmitted per second, like that. You are looking at the number of bits input. I mean your input data is digital, right? So how many bits transmitted per second by the encoding scheme. But here when you are trying to transmit the signal, you will be encode that bit using some signal element, right? So that is some high voltage, positive and negative voltage, or simply same polarity but a different voltage level. So that when it comes to baud rate, we are looking at the signaling part, like the signal element only. So for a given sequence of bits, when you are trying to convert those bits or encode those bits into a signal, look at the signal and how many times the signal level is changing, like plus 5 to minus 5, minus 5 to plus 5, like that. How many times the signal element is changing, or plus 5 to plus 2. That means I am giving plus 5 voltage for 1 bit and plus 2 voltage for another bit. So how many times that variation is happening, and that is what we call as the baud rate. And this will depends on the nature of a digital encoding technique, and that we will see. So different techniques are there. So after learning that techniques, you will understand how we can come up with the modulation rate or baud rate for a given technique. So see, even though it is digital signaling, we are using the term modulation rate, and don't be confused with the other analog part. So this is the terminology used, that's all. The baud, so you can simply learn it like bit rate and baud rate. So that is a standard terminology, and in some textbook this baud rate they are calling as modulation rate also. So the modulation rate is expressed in baud, particularly baud per second, just like bits per second, baud per second, or simply baud per second you can call as baud. Okay, which means the signal elements changed per second. Okay, or is the signal elements per second, like that. And finally, two more terms, that is a mark and space, for historical reason referred to binary 1 and 0 respectively. That means conventionally, historically, this 1 and 0 are called mark and space. Okay, so for whenever there is a 1, we can represent it by a mark, and 0 means absent of that mark, that is space. Okay, like that also simply you can represent your binary data. Okay, that is the simplest scheme. So that is a conventional terminology. So just the same data terminologies I listed here once again. Now it is clear for you what is data element, what is data rate, what is signal element, what is signaling rate or modulation rate. 4 terminologies mainly you have to think about, and the unit and the definition. For data element, bits, right? How many bits per second, that is a data element. So for signal element, the voltage pulse of constant frequency, phase and amplitude. Okay, the signal element, if the input data is digital or input data is analog, accordingly for digital data a voltage, a pulse of constant amplitude, and for analog data a pulse of constant frequency, phase and amplitude. And this you will be clear when we are dealing with the techniques. Okay, so signaling rate or modulation rate, the signal elements per second. Okay, that is baud, just like bits per second. Here you are using the term baud. So basically signal element means for a particular signal element you are representing a particular data element. So there is a mapping between data element and signal element. Definition and all we already seen. Okay, that about, just go through it. Now interpreting the signal at the receiver. So once you send a digital signal, now we are looking at the receiver part, the terminologies that we are using at the receiver side for interpreting a given digital signal. First, the receiver must know the timing of each bit, right? So where the high and low are coming, accordingly he has to differentiate the signal to get the original, that means the decoding part, to get the original data. That is, the receiver must know with some accuracy when a bit begins and end. Okay, some kind of clocking is needed. And we will see how this clocking is achieved. Either you can use the physical clock itself at the sender side and receiver side, which are fine tuned, or the technique itself is giving some hint about the clocking. So without using any physical clock, additionally you can achieve this clocking. Now second, the receiver must determine whether the signal level for each bit position is high or low. That is because when you are sending that signal with some high voltage and low voltage like that, on the way the signal may suffer from attenuation and other such distortions, and whenever there is such attenuation kind of thing is happening, even though you are sending with a high voltage level, it may degrade to a low voltage. So like that, a clear distinction of or the determination of the signal level for each bit position to be high or low is needed. Then only he can decode the information from the signal. Okay, so normally we will be having some threshold value. So those voltage level above that threshold we will be treating as 1, and below that threshold we will be treating as 0, because we can't particularly say that say plus 5 for 1 and minus 5 for 0, something like that, because definitely that attenuation, those things will be there. So you have to fix a threshold. Above that threshold you have to interpret like 1, and at the same day you have to deal with the errors also, so that should not happen. These tasks are performed by sampling each bit position in the middle of interval and comparing the value to the threshold. This is what I said. And similarly, whenever we have a duration of the bit, that is 1 by r, and decode that information, that is what we call as sampling. And sampling, again some more explanation needed for this term that we will see in subsequent part. So right now you understand, like you are trying to infer the data from the signal part. Okay, do that process at the middle of each interval. Okay, so if you are looking at the bit interval, do this process at the middle, and also compare that voltage level with the threshold. Okay, so because at the end, if you are looking at the end part, there may be some distortion and you may not get the correct voltage level. So that is why you are doing that decoding at the middle of each bit and comparing that value with the threshold. And definitely there are noise and other impairments that might lead to errors too. So everything you have to take care at the receiver side when you are decoding the information. The clocking, three things we discussed: the clocking and determining whether the signal level high or low. That is, do this process at the middle of the signal of the bit duration and compare the value with the threshold. Now means at the receiver side itself, these are all the process involved, but what are all the factors that determine how successfully the receiver is able to interpret the incoming signal? So the success of the decoding process depends on certain parameters, like mainly we have 3 parameters: the signal to noise ratio, the data rate and bandwidth. So you have to fix all these parameters in such a way that there is minimum means you have to end up your process in a successful way. There is minimum distortions, there is minimum error. Okay, so for the smooth functioning at the receiver side, you have to take care of the signal to noise ratio, the data rate and the bandwidth. All the three factors are affecting the receiver's receiving quality. And how it is so? With the other factors other than these three held constant, the following statements are true. So for example, an increase in data rate increase the bit rate. Okay, so when you are looking at this statement, make other data, you are looking at data rate only, the signal to noise ratio and bandwidth you have to keep constant. That is what this line mean. So making other two parameters constant, if you are looking at the data rate, if you increase the data rate definitely there will be increase in bit error rate, right? Because you are trying to send more bits per second. Increasing data rate means number of bits transmitted per second is increased. Definitely there will be more probability of bit error rate will be high. So that is directly observable. And similarly another one, an increase in signal to noise ratio. Signal to noise ratio is increasing means noise is getting small and signal is more dominating, right? So definitely the bit error rate will decrease because of less noise. An increase in bandwidth allows an increase in data rate, right? If you increase the bandwidth, that will increase the data rate. If you increase the data rate, ultimately it will increase the bit error rate. So we want high data rate, high bandwidth, everything, but try to keep a balance so that you can control that error. And make a try to ensure a very good value for the signal to noise ratio for the underlying medium. There is another factor that can be used to improve the performance, that is a encoding technique you are using, encoding scheme. The encoding scheme is simply the mapping from data bits to signal element. So what technique you are using for that mapping, that also determines the quality of the reception. Okay, that is similarly that means that we will see different encoding techniques. So by varying the encoding technique, there is some that is having some contribution to the bit error rate and all. Okay, so if you are looking at the bit error rate, it is the most common measure of the error performance on a data circuit and is defined as a probability that a bit is received in error. With what bit error rate of a particular data circuit means the probability at which you can expect a bit to be in error. Okay, so it is also called a bit error ratio. Now so this is again something you have to deal at the end of this module, but as it is given at the beginning of your textbook, I am explaining at this point. So the evaluation criteria, so after learning all the signal encoding techniques, the 4 categories, subcategory, everything, how you will evaluate a given technique, so that for a given application, suppose you are a communication engineer, how efficiently you are going to take a given technique. Okay, means when you are while looking at your decision making process, what are the parameters you have to consider to evaluate a given encoding technique. Okay, even though it's a general terminology for all the 4 cases, whether it is encoding, modulation, everything, the evaluation criteria could be like this. The first one, this is something more technical actually, just to have a brief idea about it. It's a signal spectrum. You know what is spectrum? After doing your encoding technique, you are converted it into a signal. That can be an analog signal or a digital signal, whatever it is. So there is a spectrum for it, right? That is a range of bandwidth, the highest range of frequency. Spectrum means the width of bandwidth. The bandwidth is a range of frequency. So the highest frequency minus lowest frequency. So that is having an impact on the quality of the signal transmission, reception, everything. So the technique encoding technique which you are using is going to determine this also. So make your technique in such a way that you have a signal spectrum. You have to consider 2 parameters here. Try to avoid high frequency components and also try to avoid direct current DC, because these two are having some negative impact on the smooth functioning of signal transmission. So a lack of high frequency component, high frequency, you can see that means suddenly a particular frequency component is high, so definitely the spectrum will be high. So the entire spectrum is dominated by that particular high frequency component, means less bandwidth is required, right? Of course. So that is what we are preferring. So make your encoding technique such that it is not going to produce any high frequency component, so that for a given bandwidth, the less bandwidth is enough to send your information. So that is the idea. And the second point is lack of direct current, and that also some technical details are there. So make sure that there is no DC component in your after performing your encoding technique. And you know what is the difference between DC and AC? When it comes to DC, it's a fixed voltage that is not varying. Okay, so we will see certain signal encoding are having some tendency towards giving some DC component, and that is again not a desirable feature. So with the DC component to the signal, there must be direct physical attachment of the transmission component. And if there is no DC component, AC coupling via the transformer is possible. This provides excellent electrical isolation and reducing interference. So don't here there are many technical jargons that is and the details and all I too didn't get anyway. I just listed only. Electronics people will be having more idea about it. So whatever it is, no need to think about all those things. Come up with a signal encoding technique with the so that this is a property, like there's try to make the system in such a way that there is no high frequency component. No means it is not possible to eliminate it completely, but at the same time try to make the free avoid it. Okay, lack of high frequency component and lack of direct current is what is desirable. So accordingly design your encoding technique, or accordingly choose a encoding technique which is providing these two features. Okay, and another one, of course, clocking that I already told you. Clocking, we need it for synchronization, because when the sender is sending sequence of bits in the form of signal, at the receiver side, the receiver has to decode the information back, right? So the speed at which the sender is sending and speed at which the receiver is receiving the information, and everything matters. Like the receiver should know where a particular signal is beginning and ending, and for all those things we need the clocking. That is terminology used for that is synchronization. So the sender and the receiver has to be synchronized each other with the help of a clock. A mechanism is needed to determine the beginning and end of each bit position. Okay, so ultimately where it is beginning and where it is ending, and the why it is needed, it is because, you know, if you are sending a sequence of bits, suppose all are ones, so basically the simplest mapping is a direct one-to-one mapping, right? One with a high voltage, 0 with a low voltage. When you are encoding like that, simply think about that situation. You have a sequence of ones, say 100 ones are coming, and for all 100 ones you can give only a particular voltage level, because for 1 you fix the voltage level like a +5, for 0 it is say -5. Now you are not able to switch the signal level, right? Simply if there are 100 ones sent by the sender, there is no interleaving zeros. Okay, continuously ones are coming, everything will be represented by a particular voltage. So now at the receiver side, how the receiver will be understanding that there are 100 ones in it, because it is simply seeing a just a line like a high voltage is coming. So where a particular bit is beginning and where it is ending, that is something you have to differentiate. So that means even though it is coming like a sequence of ones, the technique should be able to differentiate first one from the second one, like that, and third one from the first. That is where the technique is having an important role. Otherwise, simply for one voltage represent 1 and another voltage represent 0, that is enough. More than that, why we need different technique, that is because of this clocking issue. Okay. So one rather expensive approach is to provide a separate clock that lead to synchronization of the transmitter and the receiver, both sender and receiver side, same clock you are fixing, and accordingly by looking at the clock duration you are differentiating the bit. Okay, that is okay, but that is costly, right? Because this separate clock, physical clock, you have to provide And why don't you think about this technique more intelligently? So there is an alternative is to provide the synchronization that is based on the transmitted signal, which can be achieved with a suitable encoding technique. And we will see, because we have certain encoding techniques like a Manchester encoding, differential Manchester encoding. These techniques are providing excellent clocking also. We don't need to depend on a separate physical clock for achieving this synchronization. Okay, so the terminology synchronization, clocking, physical clock, as well as the technique, and that is providing the logical clock. Those things are clear for you. So that is another evaluation criteria, whether we have to use a physical clock or the technique itself is providing a clocking some kind of synchronization or not. Now when it comes to error detection, normally error control is something very important when it comes to data communication. And that is because we can't see, because whenever you are sending your data, digital or analog into digital signal or whatever it is, on the way definitely error can happen, right? So on the way we have the underlying transmission media, and external disturbances are there, interferences are there, even some unavoidable situations like thundering, those things can also happen. So definitely chances are there for the signal to change its value, like a high voltage may be changing to low voltage or something, sequence of bits may be corrupted, anything can happen, right? So an efficient technique should be there for controlling this error. So there are two phenomena called error detection and correction. And correction is normally more costly, like you have to detect and at the same time you have to pinpoint it and you have to correct it also, right? So definitely it will be a more complex and more costly approach. So most of the time in if you are looking at computer networking and all, instead of doing this error correction, we are preferring error detection, because if we can detect the error, we can inform that to the sender, and so that the sender can retransmit the signal, right? So whenever you send something to the receiver detected that there is an error and it don't know what is the error and it is not able to correct it also, it will simply inform the sender there is an error in the data that is received, so please resend, so that the sender can resend the information. So and now the time and the effort taken for detecting the error and retransmission of the original signal is normally very less compared to the time taken for the correction of the error at the receiver side. Okay, so this is a very important concept. That is why in computer network and all, we are preferring error detection than error correction. Okay, because the complexity and the time incurred in correcting an error is more compared to detection and retransmission. So detection and retransmission is what we preferred over correction in computer network, but there are other situations also where we are going with the correction. So there are many techniques proposed for error detection, particularly like checksum is there, cyclic redundancy check is there, and I think you are last module or second last, fifth module is dealing with those error correction and detection techniques, and those techniques and how they are working, that we will see at that point. And in the very first beginning of our this subject, I given you that layered architecture, like a physical layer, data link layer, network layer, like that 7 layers. And I told you, like in data communication mainly we are dealing with the physical layer and some part of the data link layer. So mainly if you are looking at this error detection as a functionality, it is done by the data link layer. So it is typically the responsibility of the layer of logic above the signaling level. The signaling level is nothing but the lowest level, that is a physical layer. And above physical layer we have the data link control or data link layer, and that is what is dealing with the error detection normally, that we will see. And even in your computer network, those layered architecture, all the layers, everything you will study in your higher semester, and that time you will see it. So right now we are in the physical layer only, and the signaling and techniques, everything is dealt by the physical layer. But when it comes to error detection, it is mainly the responsibility of the data link layer above to the physical layer, but at the same time the signaling technique itself are having certain properties in such a way that it can support the error detection, okay, to some extent. So however, it is useful to have some error detection capability built into the physical signaling encoding scheme. So that is also another criteria by which we can evaluate the signal encoding technique, that is whether the technique is having some error detection capability or not, okay, whether the technique is providing some synchronization or not, whether the technique is achieving these features. So like that you can evaluate, okay. So this permits the errors to be detected more quickly because we are having some support at the lower layer itself. At the same time, the same detection will be running out at the data link layer also, but if we can detect it at the physical layer, that is more good, okay. Now signal interference and noise immunity, that means given an encoding technique, how much immunity it is providing for signal noise as well as interference, okay. So certain encoding codes exhibit a superior performance in the presence of noise, and performance is usually expressed in terms of BER, that is bit error rate or bit error ratio, we saw it, right. So that is a performance measurement terminology we are using. So we need a technique which is having less bit error rate, okay, that the probability of a bit to be errored, that should be less. So that is again certain encoding techniques are exhibiting such a characteristics like noise immunity and interference immunity. And of course, the last but not the least, the cost and complexity. Although the digital logic continues to drop in price, that we already seen, like day by day we are getting the devices to be less costly, but at the same time we are not able to ignore it. Even though it is less costly, we want it more less costlier, right? So in particular, the higher the signaling rate to achieve a given data rate, the greater the cost will be, okay. So here you have to give some more attention, and I think you will understand it at the end of discussing the techniques. Higher signaling rate to achieve higher data rate. Let me try to explain, but if you are not understand, leave it. So ultimately we need a higher data rate, right? For a given bandwidth, we will try to increase the data rate maximum, and accordingly we will be sending the data. And data rate means number of bits transmitted per second. Signaling rate means number of signal changes per second, okay. Now for a given bit, how many times the signal is going to change for representing a particular bit. Suppose I have 100 bits to send, and for every bit the signal is changing only one time, then 100 will be the baud rate. Both the bit rate and baud rate will be same. Baud rate is the signaling rate, signal change rate, okay. Now suppose I am representing a particular bit, that is 0 or 1, with say 2 different signal change. That means for every bit the signal is changing 2 times. And why it is so? It is for actually achieving the clocking and error detection capabilities actually. Mainly for synchronization we are doing that. So when we are trying to change the signal say 2 times or 3 times for a given bit, suppose you are sending 100 bits, the signal will be changing say 200 times, or the signal will be changing say 300 times, okay. And when you are trying to achieve means more synchronization, error detection and noise immunity, when you are trying to add these features into your encoding technique, what will happen is you have to compromise this. Like when you are trying to improve the quality of your encoding, naturally the signaling rate will be more compared to the data rate. So as the signal rating is more and more compared to data rate, the overall encoding technique will be more complex and more costly, okay. So if you want the system to be cost effective, you have to compromise something from this side, okay. So that about it. So this they may ask you such a question, that is why I listed here, given a signal encoding technique, what are all the criteria by which you can evaluate it. So these 5 techniques are mainly given in the William Stallings textbook, and hope you have got a brief idea about it, okay. But each technique we need more attention to understand why it is preferred, and how a given encoding technique is able to achieve this particular parameter, and that we will see subsequently by understanding the signal encoding technique more and more, okay. With this I am winding up this part 2. Now in subsequent parts we will see the techniques in detail. Okay, so far we have an idea about all the four modulation schemes. I mean all the four and signal encoding schemes. Some terminologies associated with it, and right now we started with the very first one, that is a digital data and digital signaling scheme. And we saw some terminology so far and the evaluation criteria, everything, and the technique particularly we are going to see in the subsequent parts. Thank you.